After studying this module, you shall be able to know the importance of explicitly bringing risk into the analysis, learn the difference between risk and pure uncertainty, identify economic agents as being risk averse, risk neutral and risk seeker or risk lover. Evaluate the degree of risk of various risky prospects in absolute and relative terms. Let us start with the importance of including uncertainty in economic analysis. So far, the theory has tried to explain how economic agents behave under conditions of uncertainty. For instance, a firm under perfect competition is assumed to know the input prices as well as the price of its product which are given to it. Similarly, it knows the production function which yields a unique level of output for various quantities and combinations of inputs. It has to decide only on the profit maximizing quantity. In other words, the quantity that it has to decide to produce is the only endogenous variable, while the product's price as well as the prices of the inputs are parametric or exogenous to a single firm, but are decided by the model which takes into account the simultaneous acts of all the firms together with the demand for the product and the supply of inputs respectively. This process is repeated in the subsequent time periods in static analysis. The passage of time has no impact on the equilibrium values of the prices and quantities. Yet, production is a process and necessarily takes time. There is an elapse of time between the decision to produce and the finishing of the production. In other words, the decision to produce is made in one time period, but the product is available only in the next time period. Would the price of the product have remained unchanged in that next period? Take agriculture as an example. The price of the product that prevails when the decision to produce is taken is unlikely to be the price of the product when the crop is available for sale. Then again, the production function too has elements that are beyond the control or prior knowledge of the producer. For example, the weather conditions, which too affect the level of output. Disease or better pollination too affects the output. The process is marked not with certainty, but with uncertainty that has to be brought into the analysis. Producers faced with these problems as well as other firms which deal with these products further up the production chain try to protect themselves from the effects of uncertainty or even profit from it by taking recourse where possible to insurance, forward markets or speculation respectively. These are economic activities which can be explained only by analyzing the phenomenon of uncertainty. Let us now discuss the concept of risk. Uncertainty is 0 or 1. Risk is between 0 and 1. If an event happens with certainty, then its probability is 1. Non-occurrence implies a probability of 0. Uncertainty consists of binary variable occurrence or multi-occurrences. Probability x leading to 0 or probability x leading to 1. It never becomes 0 or 1. Risk is always about occurrence. For example, rain will occur with a probability 0.7 px is equal to 0.7. The event x, ins, occurrence of rain. Uncertainty is about whether rain will occur at all. Consider once again a firm under perfect competition. It faces a state of nature or environment which it cannot control, but which could affect the price of its product, the prices of its inputs as well as the production function. For example, an unexpected surge in consumer confidence can increase the demand for the product and therefore the price of the product. An unanticipated disruption of petroleum supplies could increase the price of some of the inputs, and a shift in winds could bring rain when it is needed and improve the natural productivity even though there were to be no change in the inputs. The occurrence of any particular state of nature is stochastic. This implies that there is another, that is a third element in the analysis of a firm. In the traditional theory of perfect competition, there were only two elements. The first of these was the price of the product and the prices of the inputs, which were parametric to an individual firm, but were determined by the model. The second was the level of production, which an individual firm had to decide taking into account the given product and the input prices. These prices are not expected to change from the current period at which the decision is taken by the firm and the subsequent period at which the desired quantity of output materializes. Even if the change were to occur, the change, its timing and quantum would be perfectly anticipated. This made the analysis entirely deterministic. With uncertainty being brought into the analysis, there is a third element, the state of nature, which is stochastic. In the period subsequent to the one the firm has to make a decision, it could have the effect of altering the prices of the product and the inputs in several ways depending on the state of nature that occurs. The state of nature cannot be predicted in advance, and yet the firm must take into account in order to take a decision. With these possible input and product price changes, the profit outcome of the firm's action is not uniquely determined. Instead, there may be several distinct outcomes, some of which may be negative. Under these circumstances, is rational decision making possible? If so, how would a firm, or for that matter any economic agent, go about it? It can be seen that with uncertainty, the outcome of any action will not be unique, and that there may be several possible outcomes depending on the state of nature that would occur. It may be possible to attach a probability to each of these possible outcomes, either based on some experience or a prior reasoning, such as the probability of obtaining a head-on tossing an evenly weighted coin. If this were to be the case, some sort of economic calculation is possible. This would place the economic agent in a position of risk. If, on the other hand, no probabilities could be attached to the outcomes, the economic agent would be in a situation not of risk but of pure uncertainty. The analysis in this lesson from now on will be confined to situations of risk and not pure uncertainty. The choice made by an economic agent would depend upon the degree of risk and the economic agent's attitude towards risk. Let us now discuss how we measure risk. It has been seen that depending upon the state of nature that occurs, there may be several outcomes that result from a course of action taken by an economic agent. If the probabilities can be attached to each of those outcomes, a probability density function can be defined over all the possible outcomes, so that it would be possible to calculate the expected value of the outcomes. For instance, depending upon the weather, agricultural operations can yield an income per hectare as given below in table. State of good, normal or bad. Nature of probability: weather 0.25, weather 0.5, weather 0.25. Income per hectare rupees 6,000, rupees 2,000, rupees 2,000. I is equal to 1, 2, 3. The expected value of the outcome would be given by E within bracket y is equal to sigma Pi yi, where Pi is the probability of the state of nature, I and yi is the income per hectare under the state of nature I. In this example, E within bracket y is rupees 2,000. Hence, an economic calculation is possible. However, this is only the expected outcome. The actual outcome will depend on the state of nature that will prevail and which is stochastic in nature. Hence, the actual outcome need not yield rupees 2000 per hectare, but yield either less or more. It is this which constitutes a risk. Since the actual outcome may deviate from the expected outcome with a known probability, it is possible to use a measure of dispersion about the expected value as a measure of risk. One such measure is the standard deviation. The standard deviation of the actual outcomes from the expected outcome can be used to measure the risk of this prospect. In this case, the standard deviation is rupees 2828.43. In other words, the actual outcome on an average is likely to deviate from the expected income of rupees 2000 per hectare by an amount of rupees 2828.43. This is an indication of the extent of risk. This can be compared with another prospect involving another crop, which is outlined in this table. State of nature: good weather, normal weather, bad weather. Probability for each one of them is 0.2, 0.6, 0.2. Income per hectare for each one of this is rupees 2000, rupees 1500 and rupees 1000. I is equal to 1, 2, 3. In this case, the expected outcome is rupees 1500 and the standard deviation is rupees 316.23 per hectare. Here, the expected outcome of the prospect is smaller, but so is the average deviation from it and hence the risk. How can the two prospects be compared and which will the firm choose? There is a way to compare the two risky prospects, but that by itself will not tell us which one the firm will choose. That choice depends upon the firm's attitude to risk. The risk factor, the standard deviation, must be placed in perspective to its expected outcome of the prospect. This can be done by taking the ratio of the standard deviation of the outcomes to the expected outcome of the prospect. This is the coefficient of variation, that is CV. In our two prospects, the coefficient of variation are rupees 2828.43 by rupees 2000, which is equal to 1.414 or 141.4%, and rupees 316.23 by rupees 1500, which is equal to 0.211 or 21.1% respectively. Notice that the first of the two prospects considered here has higher expected income per hectare outcome than the second one, but that its expected income outcome is considerably more variable and in that sense entails more risk. Which of these two alternative prospects would a firm, or for that matter an economic agent choose? Would it go for the higher expected outcome even though it is more risky, or would the second prospect with its lower expected outcome and lower risk be favored? Which one would you choose? Different agents will make different choices depending upon their preferences, incorporating their attitude towards risk. It is to this that we now turn to. First, however, a note of caution regarding the coefficient of variation, that is CV, has to be sounded. It is a useful measure because the same units of measurement occur in the numerator as well as the denominator and cancel out in the process of division, so that the resulting measure is a pure number independent of the units of measurement. This enables a comparison of diverse prospects. However, the CV can be calculated only if the expected value of the prospect is not 0. In the first example taken, one of the outcomes was negative. If the probability distribution were to be different and the expected value of the outcome were to be close to 0, the CV would not have been meaningful. Attitude towards risk. An economic agent's preferences map the attitude towards risk and start with its utility function. The utility function that is used departs from the one that was used to map an economic agent. Individuals' scale of preferences using indifference preference analysis of demand, even though it seems similar. Characteristics of the utility function. An economic agent is assumed to be able to compare any two prospects and order them according to his preferences or indifference. For example, if there are two prospects A and B, the agent can say whether A is preferred to B, that is A greater than B, or B is preferred to A, that is B greater than A, or whether he is indifferent toward A and B, that is A indifferent to B, where greater and indicate preference and indifference respectively. This is the axiom assumption of completeness. These preferences are assumed to be transitive so that they are consistent. If B is greater than A and A is greater than C, then B is greater than C. Transitivity applies to indifference as well, so that if A is greater than B and B is indifferent to C, then A is greater than C. This is the axiom or assumption of transitivity. If there are two prospects A and B, and if there is a third prospect C such that A is greater or indifferent to C and C is greater or indifferent to B, then there is a probability P such that PA plus within bracket 1 minus P into B is indifferent to C. As the value of the prospect C increases from prospect B to prospect A, the value of probability P 2 increases from 0 to 1. This is the axiom assumption of continuity. Finally, independence of irrelevant alternatives is assumed. This leads to Neumann-Morgenstern utility function. With such an utility function, it is meant that for any individual agent, the preferences can be represented by a real number u within bracket x for each outcome x, such that A is greater than B if and only if E within bracket u within bracket A is greater than E within bracket u within bracket B within bracket where E within bracket u within bracket A within bracket is equal to E bracket u bracket P1 x1 plus P2 x2 plus P3 x3 plus up to Pn xn bracket bracket. The xi are the mutually exclusive outcomes which occur with their respective probabilities Pi, with I taking the values ranging from 1 to n. Similarly, E bracket u bracket B bracket bracket is equal to E bracket u bracket P1 Z1 plus P2 Z2 plus P3 Z3 plus up to Pm Zm bracket bracket. The Zi are the mutually exclusive outcomes which occur with their respective probabilities Pi, with I taking the values ranging from 1 to m. This utility function can be replaced by another utility function, which is a linear transformation of the first utility function. This is in contrast to the ordinal utility function, wherein one ordinal utility function can be replaced by its monotonic transformation. In this sense, the Neumann-Morgenstern utility function is cardinal. In addition to the above assumptions, that is axioms, it shall be assumed that the utility functions are twice differentiable. On the basis of the assumptions made, it is possible to show that the utility functions can depict risk averse, risk neutral and risk loving preferences according to whether the utility functions are concave, linear or convex with respect to the size of the outcomes. Now, we will discuss the utility function of a risk averse economic agent. Consider an individual whose utility function with respect to income is given by u is equal to log 10 y, where u is the individual's utility and y is the income. This utility function shows that the utility of the individual increases with income, but with a decreasing rate. This function has been shown in the figure. Assume that this individual faces a risky prospect of either getting an income of 2 units with a probability of 0.5 or an income of 8 units with a probability of 0.5. His expected outcome, that is income, is 5 units. That is, E within bracket y is equal to bracket 0.5 into 2 plus 0.5 into 8 bracket, which is equal to 5 units. However, he gets either an income of 2 units or an income of 8 units. From the utility function, it can be seen that he would either get a utility of 0.3010 with a probability of 0.5 if he were to get an income of 2 units, or alternatively he obtains a utility of 0.9031 with a probability of 0.5 if he were to get an income of 8 units. The expected value of utility is 0.6021, that is E bracket u is equal to bracket 0.5 into 0.3021 plus 0.5 into 0.9031. A comparison of a risky prospect with an expected income of 5 units with a certain prospect, that is probability equal to 1, which also yields an income of 5 units, is illustrative. A prospect of a certain income of 5 units has a utility of 0.699, whereas the risky prospect with an expected income of 5 has a utility of only 0.6221. This is because although the expected income is 5 units, the economic agent or individual actually gets either 2 units of income or 8 units of income. The utilities pertaining to those incomes are 0.3021 or 0.9031, each occurring with a probability of 0.5. Clearly, the individual or economic agent prefers a certain prospect of 5 units of income to a risky prospect of an expected income of 5 units. In this case, the expected utility of the risky prospect is less than the utility of its expected income had it materialized. That is, E bracket u is less than u bracket E bracket y and close bracket. This is because the utility function is concave to income excess. Utility increases as income increases, but at a decreasing rate. Technically, the first derivative of utility with respect to income is positive and the second derivative negative. It is this that makes the utility function concave. For a strictly concave function, a chord connecting any 2 points of the curve will lie wholly below the curve except at those 2 points. This implies that the expected utility of any risky prospect, which is given by E bracket u, is equal to P1 u bracket y1 plus P2U bracket Y2, where P1 plus P2 is equal to 1 will necessarily be less than the utility of the expected income U bracket E bracket Y bracket, where E bracket Y is equal to P1 Y1 plus P2 Y2, and where P1 and P2 bracket 0 and 1. In general, sigma PIU bracket YI is less than U bracket sigma PI YI bracket. This type of utility function characterizes an economic agent or individual who is risk averse. In this utility function, a decrease in income from the expected level of 5 units to 2 units of income weighs more on economic agent's mind than an equivalent increase in income from the expected level of 5 units to 8 units. Since the utility function is continuous, it is possible to find an income which and the risky prospect given above, the individual or the economic agent is indifferent. From the utility function, it can be seen that a utility of 0.6021 corresponds to an income of 4 units. Then a certain income of 4 units is a certainty equivalent of the risky prospect. Note that the certainty equivalent of 4 units is less than the expected value of the risky prospects of 5 units. This is a characteristic of an utility function of a risk averse individual. In this case, the economic agent will be prepared to pay a risk premium of up to 1 unit. The maximum of the risk premium is the difference between the expected income of 5 units from the risky prospect and its certainty value, provided that this risk premium ensures the economic agent of a certain income of at least 4 units. This explains why economic agents seek insurance. Let us now move on to the utility function of a risk neutral economic agent. Now, consider a risk neutral economic agent. Such an agent prefers the higher prospect to a lower prospect and is not affected by the element of risk. His utility function is linear, with utility increasing at a constant rate as income increases. Consider a utility function such as u is equal to y. In this case, the chord between any 2 points coincides with the utility function. Consider once again the risky prospect, wherein the mutually exclusive outcomes are 2 units of income with a probability of 0.5 and an income of 8 units with a probability of 5 units. Here again, the expected value of the outcomes is an expected income of 5 units, that is E within bracket y is equal to bracket 0.5 into 2 plus 0.5 into 8 bracket units is equal to 5 units. The utility of the expected income u bracket E bracket y bracket close is 5, and the expected value of the utility of the outcomes E bracket U bracket 2 is 5, with E bracket U is equal to bracket 0.5 into 2 plus 0.5 into 8 bracket closed is equal to 5. Here it can be seen that the certainty equivalent of the risky proposition coincides with its expected value. There is no risk premium, with the individual being indifferent between a certain prospect and the expected income of a risky prospect. The individual or economic agent will prefer a higher income to a lower income. Now, let us discuss the utility function of a risk lover, seeker, economic agent. Now, consider a risk lover or a risk seeker. His utility function is convex to the income axis. Consider an utility function such as u is equal to y square. From figure, it can be seen that it is convex to the income axis with the chord connecting the points corresponding to incomes of 1 and 3 units, lying over the utility curve between the income points 1 and 3. The first derivative with respect to income is positive and the second derivative too is positive. Consider a risky prospect with mutually exclusive outcomes of an income of 1 unit with a probability of 0.5 and an income of 3 units with a probability of 0.5. In this case, the expected income of the risky prospect, that is E within bracket y, is 2 units of income. It can be seen that the utility of the expected income of 2 units of income is 4. However, the expected utility of the outcomes E within bracket u is bracket 0.5 into 1 plus 0.5 into 9 bracket is equal to 5. It can be seen that the expected utility of the risky prospect is actually greater than the utility of the expected income. Consequently, the economic agent will prefer this risky prospect to one with a certain income of 2 units. This then is the utility function representing the preferences of a risk seeker. An excess of income from the expected income of 2 units to 3 units weighs more on the agent's mind than an equivalent decline from the expected income of 2 units to 1 unit of income. The expected utility of outcomes, which is 5, corresponds to an income of 2.236 units of income, which is the certainty value of the risky prospect. The risk seeker would be prepared to pay up to 0.236 units of income in order to participate in this risky proposition. This explains why economic agents like to gamble in various ways. So far, only pure cases of risk averse, risk neutral and risk seeking attitudes towards risk have been taken. However, it is possible for an individual to display all these attitudes. This explains why economic agents voluntarily seek to insure their houses and jewelry and yet gamble. Till their income or wealth reaches a certain level, for instance, the agent is risk averse. Thereafter, on attaining higher levels of income, he becomes either risk neutral or even risk seeking. It shows that the utility function is initially concave to the income axis and then becomes convex. There is a point of inflection at the point where the curve changes its character from being concave to becoming convex. This corresponds to the income or wealth at which the economic changes his attitude from being risk averse to being a risk seeker. To simplify the analysis, in the examples taken, there were only two mutually exclusive outcomes with probability of 0.5. The concepts are applicable to prospects of multiple mutually exclusive outcomes with varying levels of probability. However, the sum of all probabilities is unity, that is sigma pi is equal to 1. In other words, there is a probability density function defined over all the mutually exclusive outcomes. Let us now recapitulate what we have studied in this module. Traditional economic analysis does not take into account the states of nature which causes uncertainty and affect variables which influence the decision making by economic agents as well as the outcomes of their actions. Consequently, the theory can neither explain the decision making of the economic agents nor explain phenomena such as insurance seeking and gambling. Under different states of nature, the outcome of any action by the economic agents will not be unique, but will vary. If no probability can be attached to the various outcomes, then the situation is one of pure uncertainty. If, on the other hand, probabilities can be attached to each of the many outcomes, so that a probability density function over the various outcomes can be defined, the economic agent is operating in a situation of risk. Here, economic calculation is possible and expected values and measures of dispersion of the actual outcomes about the expected values, such as the standard deviation, can be estimated. Risk can be defined as the degree of dispersion about the expected values as well as the ratios, the coefficient of variation. These measures also indicate the trade-off between what the economic agent will get and the risk attached to different alternative risky prospects. The choice that an economic agent will exercise will depend on his attitude towards risk, which can be risk averse, risk neutral or risk seeking. These attitudes can be mapped by Neumann-Morgenstern utility function. Risk averseness, risk neutrality and risk seeking is represented by utility functions which are concave linear and convex respectively. A risk averse agent is prepared to pay a premium, the maximum amount of which is the difference between the expected value of the risky prospect and its lower certainty value in order to get an assured income or wealth at least equal to the certainty value of the prospect. The risk seeker, on the other hand, would pay to undertake risk. The maximum amount that he would be prepared to pay would represent the difference between the expected value of the risky prospect and its greater certainty value. The same individual can display risk averse, risk neutral and risk seeking behavior.